In this work, it's about current transform and his application as sensors current. A current transformer is a type of instrument transformer that is designed to produce an alternating current in its secondary winding, which is proportional to the current being measured in its primary. Our current transformer design has 5 turns in the primary winding and 78 in the secondary winding. The motivation that this project, the main motivation to performance this work is view the difference between the seeing and theory calculation and the values measure physically, as well as apply knowledge obtained in classroom applied to the real life.
Diagram to blocks. First appears the current transformer with his primary winding connected to electric network in series with a charge of 10 ohms. The secondary winding is connected to a charge to get a sinusoidal voltage in the secondary. Second appears the precision rectifier that rectifies the sinusoidal wave at output of secondary winding. There appears a charge followed by a capacitor bath connected to ground to convert the rectifier wave in a direct current level voltage. Finally appears an operational amplifier to get a direct current level voltage between 4.5 and 5.5 volts.
First, in the simulation as having a current transformer, we simulation the output voltage in secondary readings with an AC power source. Second, we set an operational amplifier non-inverter to grow input voltage. Third, we set an operational amplifier voltage follower to keep the input voltage. Fourth, we set a precision rectifier or half wave. Fifth, we set a charge followed a capacitor to convert the rectifier's wave in a DC nivel voltage. Finally, we set our operational amplifier non-inverter to grow the input voltage and reach between 4.5 and 5.5 volts as output DC. Figure 1. In a red can view sinusoidal wave of secondary after first operational amplifier. In blue can view sinusoidal wave of secondary after precision rectifier. Figure 2. In blue can view the DC nivel voltage before operational amplifier. In green can view the DC nivel voltage after operational amplifier.
First, here we can view the physical implementation of circuit. We can view the 4 amplifier operationals, the capacitor, the resistances, the tips oscilloscope to make measures and toroidal arrangement. Second, we can view in green the sinusoidal wave that produces the secondary winding. In blue, we can view the same sinusoidal wave, but after the first amplifier non-inverter to reach to power up the diodes of the precision rectifier. Third, we can view the same sinusoidal wave in output precision rectifier. We can view that have the same amplitude of the original sinusoidal wave. Fourth, we connected the capacitor and we can view as the sinusoidal wave is converted in a straight line that represents a DC nivel voltage. Finally, we can view both straight lines in green before amplifier, no inverter, and in blue after amplifier, no inverter. Our current transform has losses by load losses that vary according to the loading on the transformer, and by no load losses are caused by magnetism current needed to energize the core of the transformer. These losses affected the output voltage in the secondary winding. Are used a load of 150 ohms connected to primary. The current in primary is 12 amperes and our relationship turns is 5/68. Hence, but physically the voltage measured is 240 millivolts. By this reason, we set our operational amplifier, no inverter, to increase this voltage until reached to power up the rectifier. Applying the formula, we was increase the output voltage in the secondary winding. In output rectifier, the amplifier is the same that the voltage increase less. After the filter, the input voltage in the last operational amplifier no inverter, the oscilloscope measured 3.668 volts. To reach the range voltage, we apply a configuration no inverter to increase the input voltage. We had very complication in the physical implementation, but expect that our oscilloscopic measuring coincide with of theory calculates. Never consider the losses by the load in head and the losses by the magnetizing current, the wire and the core. This situation forces us to add components not provided in the original design to meet the necessary requirements in the project.